that means what's coming into read register 2 is 0, which if you look at the green card, that happens to be registered $0. So this is going to be always 0. So the second input to the ALU is going to be always 0. The first input to the ALU is going to be some register. So if that register is a 0, then we do the reg. So that's what F2 does. Well, that's a tough question to answer, how you would do it. Basically what you want to do is you want to figure out what exactly is on each one of these lines. And, I mean, just writing pen, what exactly is this in this line? It's going to be reg x, where x is specified by bits 25 through 21. And what's on this line is going to be 0. So if reg x equals 0, then I do a grant to the normal. Because it says that this bits 20 through 16 are all zeros. Which is, if you look at the green cards, that happens to be registered $0.
20 through 16?
Yeah.
Oh, okay. And so that goes to region 2?
Yes.
Oh, okay.
So that happens, but the important thing is you know that is registered $0, which always contains 0.
Okay.
So it's basically the same as branch and equal, except that one of your inputs is 0.
Yo, we play Minecraft? Yeah, we play Minecraft right now? Yeah, that's crazy. No, no,
B is not right now.
it's the same.
Yeah, yes, yeah.
Okay.
That's one way of doing PEZ. Yes.
We have to beat the end before we touch the movie. Hardcore. Hard.
Yeah, we can always bring in, I will not do it because we'll do something very similar to it today. You can always bring in the multiple ways of doing it. One way is to bring in the 0 on the immediate field, and then picking the immediate field coming in here. Another one what?
No, but number 2, like an F3, can you make up an F3?
Oh. Instead of doing that, why don't we do what we're going to do today, because I think that'll, I think you won't ask the question after that. I don't know what happened to get this thing on the screen.
We all fucked up too. Error 5.
Okay,
I'm
any
gonna get
questions?
it we did wrong.
Okay, so where are we? Oh yeah.
Man.
Where are we? We did a single cycle data pad, did a single cycle control pad, and we've basically done the processor which implements all the instructions that we have. So it is that easy to make a processor. Again, the hard part is writing the English for what exactly is happening for each instruction. Once you write the English precisely enough, then the rest is pretty mechanical to connect everything up in the right way. You may or may not need to add some process. So what we're going to do now is, let's say we're working at Mix Incorporated, and we want to add a new instruction. So I'm going to add another instruction to this process. Instruction I have a bunch that I can add. I'm going to add, I mean, this is what we'll be doing for the rest of the semester. We'll be adding instructions. So yeah, the rest of the semester is a lot of design. It becomes more of a designing course.
Yeah, you have to put
where
arrows
you're
everywhere.
actually designing and
Yeah. You have to put arrows here, here,
okay, so what I'm going to do, remember the way that you
Just put slashes through it too, but they didn't take away points from me for that, thankfully.
assembly language
I'm gonna turn it back on for
two
you.
instructions. Manipulating the stack pointer and adding
I forgot that command, yeah, that's so fucking
and then
dumb.
we did a store word, which is
Free card got a 3.3.
the locations pointed to like the stack pointer. That was in assembly language. But now that we work at Mix Corporation, we are going to say, let's add a push instruction, which will do it as one instruction, which, so let's do it. Maybe, anytime you want to do design, what you want to do is you want three you want a big desk, you want to keep this on one side of your desk, you want to keep it, you want to do the design on somewhere else, and for a single cycle, you just need two sides on your desk. For the multi-cycle, which is next, you'll need a bigger desk. But I mean, sort of, since for projection reasons, I'm just going to flip back and forth instead of having them side by side. Okay, so we want to do a push instruction. I'm just going to call it $reg instead of RD or RS or RT or whatever.
D&D Warrior. Where do I put it?
Okay, so there are multiple steps that we have to do. One step is we have to design the machine code format. We'll pick a machine code format that actually makes sense. Because, I mean, we could pick any machine code format we want, but obviously if you stick $reg in bits 0 through 5, it doesn't match any other instruction. It's probably not a good design decision because you're going to have to add a lot of data packs. So we want to pick something that is compatible with the existing design. So we have to pick a machine code. That's the first step we'll do. The second step we'll do is we'll make changes, if needed, we'll make changes to the data pack to support the push instruction. And the third step is we will select a control for this new data pack, for this amended data pack. Okay. So first step is the machine code. Okay, let us think about this. Well, actually we're going to do step 2. So what is actually done in the push instruction? Write it in English. Subtract 4 from the stack pointer. The stack pointer, looking up my green card, happens to be, I don't remember what it is, happens to be register 29. So subtract 4 from RF of 29. And just for your reference, that happens to be the stack pointer. Okay? And implicitly in this is that you're subtracting from it, so implicitly in this is that you're storing it back in RF29. Store back into RF29. Okay? So that's one thing we're doing. And something else we want to do is whatever we have in the new stack pointer, the memory location indexed by the new stack pointer, store, what are we storing into that memory location? $reg. Store $reg, which is from our register file, into mem of new $29. Incidentally, I don't think I explicitly said this, but going forward, we might write $29 instead of $SP because we're doing hardware. The fact that the convention says that 29 is for the stack pointer is less important to us. It's important to an assembly language programmer, but as a hardware designer, we really care that it's registered 29, not that it happens to be the stack pointer. So we will be writing numbered registers for the most part going forward. Instead of calling them S1 and S7 or whatever. Okay, so anything else that we need to do for a push? The answer is no. This is it for a push. Okay, so now we're ready to design a good machine code format for this. What is a good machine code format for this? $reg is going to go into memory. Let's look at this. What is the data going into memory is take by read data 2, which is bits 20 through 16. So maybe bits 20 through 16 makes sense for $reg. Everybody get that? The $reg is going to be going into write data.
Because we're pushing.
Yeah, because that's what we just wrote here. Store $reg into memo something. So we want $reg here. So to minimize the changes to this data path, maybe we'll bring the $reg in bits 20 through 16. I mean, we could bring it in another field, but then we'd have to complicate things. So bits 20 through 16 are going to be $reg. That sounds like somewhere around here. 16 to 20. That is going to be $reg. In our design. Again, we could design it another way. We just kind of be lazy and not add work for us. Okay, so that's one thing that's going to be needed. We want the register file. I'm sorry, I'm pointing the wrong place. We want the register file output to go into the mem address. Does that exist? Yeah, it already exists. The register file is going into mem address. However, it's not. Something's happening in the ALU along the way. So let's see what we can do. Actually, let's not worry about that just yet. You want to subtract 4 from RF29.
I only have this. I don't have the.
So that means we want to get 29 coming into read register 1. Okay? So that would make sense that bits 25 to 21 contain the
Computer's
29.
low. Computer's low.
Hold on just a second. 1, that's 16, 1101. Oh, that's not text. That's fine. Okay. Now your question?
We want 29 register 1 because it goes out to the ALU and we want to subtract it.
Yeah. Because we want to get this minus 4.
Oh, boy.
So we want 4 coming in here. Pardon me? Okay, that's a good, okay. There are multiple ways of doing it. One way is to just bring in 4 into the immediate field, and the immediate field is unused. Another way of doing it
I think it was a
is
registered
to
target.
actually hard code a 4
Oh,
into here.
why?
Yeah, why is it this?
I'm going to do it the other way because the homework is going to be to do it the immediate way. Okay? So what I will do is I will add a data path.
I think I have to high up.
1, 2, 3,
No, 1, 2.
Maybe I'll do it in the 10 because
plus
I
16,
get a fine point.
27. I'm not buying 1, 2, 4. It's 16, yeah. So we have 3 plus.
I'm going to
1,
bring
1,
in
1, 0. Oh, I got it wrong.
Racky.
So this is
I'm going to call that input 2. So I made that box a little bigger.
but it's 29.
That's why, again, that's one way of doing it. Okay, so we subtracted 4 from there. We want to store this result back into the register file. That path exists. Does it really exist? We want the register that is being written to be register 29. So that means either we have bits 16 through 11 be 29, or bits 20 through 16 be 29. 20 through 16 cannot be 29 because that's used for something else. So either we bring a hard-coded 29 here, or we bring bits 15 through 11. They bring 29 and bits 15 through 11. Let's do it the latter way, because we're saving the hard coding. Let's not make this much bigger. Okay, so bits 15 through 11 are going to get 29. Another way we could have done done it is bring this bits 25 to 21 into the input 2 of this mux, making this much bigger. That's another way we could have done it. But why? We might as well not add a hardware. Okay, so we just play games the machine code format to avoid adding hardware. Okay, now let's see whether this actually works. Okay. Do I need to trace through the path or yes?
You should write something.
Yeah, that's number 2. Yeah, because it's input 2 in the mux. Because we may turn the mux from a 2 to 1 mux to a 3 to 1 mux. Okay, do we need to trace the paths here, or is everybody good with that? Okay, trace the path. Yeah, should I use green or pink? Maybe I'll use pink because what? Okay. Okay, so subtract 4 from RF29. So 29 is coming on bits 25 to 21. That's good. So we're getting register 29 here. We're getting 4 here. So the green is the new path. So we're getting 4 there. We're doing a subtract. And we want to store it back into RF29. And are we bringing 29 into here? Yes, 29 is coming in bits 15 through 11. So we're getting the ability to store it back into RF29. So that's the first line of the data path. Second line of the data path, store $red. $red is in bits 20 to 16. Okay, store it into mem. So we want that into the mem data. How do we get that into the mem data? That path already exists. I mean, we designed it that way. So we gotta get that into the data. And that mem address input is the new $29. But what do you know? This is the new $29. It's the old $29 minus 4. So magically, it actually works. So we don't need to add anything. And we do it right. So we have the data path. So the changes that we made actually work. Cool. And again, for the homework, you'll make a different set of changes and get the same instruction. That homework I'll post tonight for Wednesday. Okay. Now we need to do the control. And let's see, let's use orange. Might as well just pink. There's no reason to change colors. Okay. Reg test. This mux is a 1 or a 0. 1, yeah, just see the pink. The jump mux, it's got a 1 or a 0. So what do we do for this push instruction? So what do we want our next PC to be? Yeah, PC plus 4, that's the fetch. So we want this to be a 0 and this to be a 0.
Yeah, good luck. That's it.
Okay. Again, in pink, I only did the instruction, the execute phase. The fetch phase is already a given, so I did not highlight the fetch phase. Okay, mem read. Are we doing a read of memory for a push instruction? No, so is it a 0 or an X?
0.
Why is it not an X?
Because we want it to not be.
Yeah, exactly. We don't want to accidentally, because the VLSI designer down the line, they might, if you make it an X, the VLSI designer might decide it's using the Karnaugh maps that X makes sense as a 1, and in which case you're telling the memory system to read when you don't really need to. You want to minimize the tension on the memory bus. Okay, mem to reg, that is this mux is well, just look at the bank, is it a 0 or a 1? 0, it's obvious. ALU up, what are we doing with the ALU up? Minus, good. Did I write sum or minus last time? Sum, okay, sum. Doesn't really matter. Mem right, are we doing a right?
Yes.
Yes. ALU source, that is this much. It's now a 2, so I'm going to write 1, 0 in binary. Read write, are we writing the register file?
Yes.
Yes, so that's a 1. And we could do this. So red desk is 1, ALU source is 1, 0. But one thing we have to do, since the ALU source now is 2 bits, we have to go and change the existing ones to 2 bits. So the 0 becomes a 0, 0, 0, 1, 0, 1, 0, 1, XX. Mem to red, what is that? That's a 0. Read write, that's a 1. Mem read is 0. Mem write is a 1. Branch and jump are, 0. And, ALU off is a sub, and jump is a 0. So we're done. So that is how we can design new instructions. Now, this is not something you'll be doing unless you're actually working at MIPS. You can't do that as a coder. You can't just add instructions. But we can add instructions for anything we want, and we can make. Yeah. Oh. Okay.
What about the rest of
The rest of the what? Well, this one we implicitly assume that if we pick something which is different from what the other, you go look through the appendix and find some value that hasn't been used. Let's not do that. I mean, I don't expect you to do that because that stuff it's too trivial. It's just boring. And some of these bits, let's see, bits. Bits 0 to 5, we have to actually worry about because that's the function field. So that, but again, we're going to 0 to 5, that's the function field, but we'll pick on whatever the sub-function is. We're not going to write that down because it's just a matter of mindlessly going through and figuring out what bit pattern that is. And now bits, the remaining bits are don't cares because we don't care what's in bits 6 through 10. Any questions about how to implement new instructions?
Why don't we care about
Well, why do we? Where is it going?
I don't know where.
It's part of the immediate field, which we're not using. And the control is based on bits 25 through 21 and bits 5 through 0. So the only thing that is part of is the immediate field, which we're not using for this instruction.
When is registration for?
I think in a week or two. He's asking when registration for classes.
Yes.
Could you show again what you did for ALU source?
What do you mean? Yeah, you're bringing in the number 4
Please still argue?
into this mux because we're subtracting 4.
Can you message you?
How do I
You don't
what?
miss him?
How did you write the opcode for?
Poor guy.
Well, the opcode is just a sub because we're subtracting. The opcode is a sub because we're subtracting.
I understand it.
Subtract 4 from RF29.
For ALU source?
Like some
Well,
people.
ALU source is just picking the operand. It's not about the opcode. ALU source is about what comes into this mux. the number 4 is coming in,
The homework.
which is the input 2 in the ALE.
You had to use it.
So in the mux. I'm not sure I understand the
I
question.
only did the first two. I
You
did
could
all
also
three.
add the third thing to the box, right?
Yeah, I made that mux a little bigger. It's a 3-to-1 mux instead of a 2-to-1 mux.
Yeah, you said you changed the other ALE sources to the other instruction types, right?
Yes.
What were the changes? Could you show them again?
Yeah, I showed them. From 1 bit they became 2 bits. It used to be 0, now it's 0, 0. Oh, I think I see what you're saying. I preceded it instead of
Is it?
I heard it's like another Candy Crush type of thing.
0, 1,
No,
0,
that's
1, 0, 0,
That's very real.
XX. Is that what you meant?
Kind of, yeah.
Okay. Yeah, I just appended it instead of writing over it.
What?
But you could write over it if you want. Okay, is there a question there or is there, no? Okay. Everybody good? Yeah.
Why do you write 29 hundreds from 25 to 21?
Because when designing the data pad, I needed 29 in multiple places.
I don't know.
Let's put our English up. I needed 29.
Nice, good job, bro.
Oh, so you have to
Um,
follow.
Well, the 2 places I'm putting it in, one place is 25 to 21, because I want to read register 29, so it's subtract
Look at the
4.
requirements.
Another place I needed it because I wanted it to be,
No.
it's 11 through 15, I wanted that to be the destination register because I'm storing it back into RF29.
What is your requirement?
When you were drawing the pink line, you started like when you were doing the big data one. Yeah, and you came up to ALU. You took the down path rather than the right path, and then went back into the register, and then you were able to go into data mount.
Yeah,
But how did you have to put the down path?
because I wanted a path that goes, I looked at this diagram and I saw that there was a path which goes from there into the right data on the memory, and I just used the existing path. If such a path doesn't exist, then either I could have made a better design, or that the better design is not possible and I would have to add some data paths. I mean, as working for MIPS, we can always change the data path. We want to minimize our changes, so we try to be compatible with the existing architecture.
Are we gonna do another one?
No, you're going to be doing many in the homework. What? As your. Okay.
Yeah. Right now, storage.
Okay. Let's see. You can do one more request, provided I have another figure.
I have one.
No, I need 2 more, but let's see, I
I
might
have
have.
2 more.
You're good. I definitely have one more. I have 2 more. Yes, I have 2 more. Okay. Actually, I have 3 more. Okay, so I can screw up one. Okay, what should we do? Let's do this one.
I hope he does join. Nothing.
Let's do, do you have any in particular that you want to do, or? Okay. Let's do execute indirect register. Dollar register, and I'll tell you what it does. Immediate. It
Oh,
executes
I finally got my degree, bro.
instructions instruction
Like BCC degree.
in $reg.
Finally. Finally
Okay?
something.
So basically $reg contains some instructions if you want to execute.
You could have gotten a horrible degree.
Let me first make sure that this is actually doable. Give me 30 seconds to think about it.
Oh my god. Finally. I'm sleeping myself for 2 days.
No, this doesn't make sense. Okay, forget that one.
You getting epilepsy?
Oh, the healing bird, are you serious?
Let's see. Come on, you asked me a question, so why don't you give me an instruction that you want me to do? Yes. Pop, that's a very good question. Actually, I asked that in the test once. But let's think about pop. What is pop actually doing? Pop, it does, what is it writing? It's going to change the stack pointer.
Change stack pointer. We're also, what's it called?
It's gonna, yeah, I mean that's what changing the stack pointer kind of does. But is it what hardware is it going to be writing? It's going to be also writing the register file, right? Because you're popping something from memory and sticking it in the register file. So that means that you need a 2 write port register file. So that's not doable. So that was the easy question on one of my past finals. Why they do this or say why it's not good, it's doable. Well, it's doable if you make this a register file, a 2 write port register file, but that's something we normally don't do. So pop is it's a great question, but we're not going to do it. Actually, you know what? I know you want more examples, but let's go on, and then we'll do more examples after. Let's go on to some performance and multi-cycle, and then we'll come back and do more examples if needed.
Yeah.
Because I think a lot of this it really makes more sense to actually do it than just see more examples. Okay, so now we've designed, the architecture team have designed the single cycle data path.
Okay.
So now what do? We want to sell this chip. So we send it to the VLSI team, the team that actually lays out the chip, and they're going to evaluate, they're going to do a bunch of things. One thing they're going to do is they're going to lay this out and convert this all into transistors. And you know from 160 how to take each one of these and represent it, using the transistors. In practice, there's going to be libraries for everything. People do not design 32-bit ALUs. There are 100,000, maybe not 1,000. There are 132-bit ALUs out there, and when you have a big screen and you just pick one of them. And they're all going to be different. And the differences between the ALUs are going to be like the size and the dimensions. Some could be rectangular with very long. Some could be like a square, and they're going to be different sized depending on how you lay it out on the chip. Thus, they're going to have different functionality. Some ALUs will be faster, but need less power. Faster but need more power. Some will be slower and need less power. It's a lot of trade-offs. So you, the VLSI designer, have to say which ALU do I pick, and there's but you're not going to design an ALU from scratch. There's a library with 100 ALUs. You just sit on your screen and you say click on this one or click on that one and pop that one into place. And so you pick an ALU. Same thing for register files. Trade-offs. Pick the register file that you want. Pick muxes are easy. So we pick all the elements that we want and we stick it on our chip. We the VLSI designers. And that's the first thing we do. That's the layout process. Then the next thing we do is you want to evaluate this thing. And we want to see how fast does it go. Okay. The way it is done, there is a tool called SPICE, which is an electrical simulator. It has 100 parameters, temperature, all these environmental parameters. And you feed in all these 100 parameters, and it'll simulate the transistor level version of this design. And it'll tell you, okay, in the simulation, this is how much power everything takes. This is all the problems that can occur in this design. This is how fast everything is, and then you can do additional analysis of this chip to see does this meet my resistance requirements? Is it fast enough? Is it low power enough? And if it doesn't, then I'll go back to the architecture designer, and typically you would be made multiple iterations. You come back to the architecture designers and say, this is too slow. You have to do something. So and then the architecture designer will change the design slightly to make it a little faster. But let's talk now about, assuming we've done the SPICE simulation, we have timings for everything, let's talk about how we figure out the clock rate for this chip. Okay. And I'm going to pull up a diagram from before because that will make things easier. If I still have it. Yes, I do. So let's use this diagram from before. And on this diagram, I'm going to put the results that my SPICE simulation gave for the timing. Okay? So I'm going to say mux is, can you read this purple? No. I want to make it reasonably fine print because otherwise the colors will bleed. Two. So let's say all muxes are 2 nanoseconds. By the way, the figures that I'm using are somewhat representative of about mid-1980s figures. The reason I'm using mid-1980s figures and not 2024 figures is that they're nice single-digit numbers in nanoseconds. Today it's like 75 picoseconds, and I don't want to write 2 digits. I want to write 1 digit. The ratios of the numbers are still approximately the same, but the numbers are much, much faster today. But we're talking about the concept, not about the actual numbers, which are less important. So those are, the muxes are 2 nanoseconds. Any other muxes? No. Okay, so let's say the control is 3 nanoseconds. 3 nanoseconds. Okay, let's say the register file, to read a register file is 8 nanoseconds. To write the register file is 12. ALU is 15, let's say. Memory is slow. Oh, an adder. An adder is, let's say, 8. 8.
Adder is 8.
Shifting is essentially 3 because it's just playing games with wires. Same for a sign extend, so that's 0. The PC, let's say that reading that is a 0, let's say. Let's say that comes for free. So what's left? In memory, let's say writing memory is going to be 40. And reading memory is going to be 20. And reading instruction memory, let's say, is going to be 16, let's say. Okay, so let's say that's what our SPICE simulator determines. Now we want to figure out what the clock rate is going to be of this chip. Okay? So how do we figure out the clock rate? The way we figure out the clock rate, well, first I need a piece of paper. The way we figure out the clock rate is we figure out how long each of these instructions takes. So R-type instructions. There are 2 things which are happening in the R-type. There's the fetch, the yellow. The yellow is, okay, now I'm going to listen very carefully to the words that I use because I'm using the words intentionally in a particular way. This output is stable 2 seconds after the rising edge. Okay? So this is stable, let me point, this is stable at 2. Now this is stable, it has multiple inputs. It has this input and also this input. This input is ignored, so that's not important. So this input is stable at 2, but this input this branch is gonna be a 0. But this input is gonna be stable at 16 plus 3. So this input is gonna be stable at 19. This is where you have to pay really close attention. This input is stable at 19. This input is stable at 2. Everybody got that? 2 and 19. So the longest input, this input is not used for an R-type. So the longest input is 19, 2 versus 19. So 19 plus 2. So this output is stable at 21. Well, if you're working with somebody and you need input from 2 people, she is giving you input at time 2. He is giving you input at time, what do we say? 19. Then are you ready to start? Come on, you're doing a job, and she is giving you her input at 2. He's giving you his input at 19. When can you start? You can't start until both of them come in.
But aren't those two working at the same time?
Yes.
So wouldn't we be ready by time 19?
Yes. However, this
Oh,
box is
but
2 more. This box is 2
Yeah,
more.
okay.
So the output is 21.
That makes sense.
Now this
got it,
input is
you got
also
it.
at 6 and 19. So 19 and 21, longer is 21 plus 2 more. So 23 is the fetch pad. So the R-type, one parameter is 23. That's for fetch. But that's not the only thing the R-type does. It does something else in parallel. So it could be the larger of 23 and the other thing it does. So let's figure out the other thing it does. Max. Okay, what else is it doing? It's doing, our R-type is orange. So it's doing something to the ALU and writing it back into the register file. So let's see how long that takes. This is stable, the instruction is stable at 16. You're reading the register, so these two inputs are stable at 20, these two outputs are stable at 24. This is no other input. So this is stable at 24, this is stable at 26, because you have this extra box. This is stable at 19 like before. No, yeah, 19. No, actually that's stable at 22. But it doesn't really matter because the longest one is stable at, I forgot what I said, 16, 24. The longest one is stable at 26. So all 3 ALU inputs are stable by time 26. 15 more. So the ALU output is stable at time 41. 43.
You think you're so smart?
And this is stable at 43. This is way less than 43. You can just eyeball it and see it's way less. So, so both inputs are available at 43. The control input for the right is also ready by 43, way less than 43. So this is all 3 inputs are available at 43 plus 12, 55. So the R-type instruction, we need at least 55 nanoseconds. The second one is the actual R-type instruction, the main part. I'll call it the main part. Okay, now we have to do another instruction, load word. Load word, again, the fetch is the same. Okay, but let's not think about the time for the main part of load word. 16, stable at 18, I'm sorry, 16, stable at 16, stable, this is stable at 24, this is stable at 16 plus 2, which, well, no, the control is 19, the data is coming in as 16, larger is 19, plus 2 is 21. So this is stable at 21, this is stable at 24, control is less than 24. So the longest of the three inputs is 24
Okay, French.
for a load word. 39. Okay, so the 39, the address is stable. You don't need data for a load word. So 39, the address is stable. At 59, the data comes out. So 59, the data is stable. 61, this is stable. This is coming in at 61. The others are much less than 61. We've already figured those out. So 73 is it. 73 equals 73. Forward. Again, we're doing a fetch. This is stable at 24. Immediate is stable at 16. The control for that is that, well, we already know that that's going to be less than 24. So let's cheat and not redo what we've already done. So this is stable at 24, and the ALU other inputs are also stable by 24. So at 39, you computed the address. The data, is that going to be less than 39? Yeah, it's going to be 24. So that's going to be less than 39. So at 39, both the address and the data are stable. Plus 40 to actually do the write. I'm going to change this to a 50. Plus 50 to do the write. So that makes it 89. Actually, I'm going to keep it at 40. 79. I'm doing this for a reason. I'm not going to tell you that reason yet. Okay, jump. Two. Well, where's the jump going? It's not the 2. I should not have said 2. 16. So this input is stable at 16. This input is not relevant for a jump. This control input is stable at 19. So the longer one is 19, 16 versus 19, plus 2, 21. So jump is 21.
Can you go through that one again? Really
Sure.
quick?
This is stable at 16. That's free. So this is at 16. This control, however, is at 16 plus 3, 19.
Why is it 16 plus 3?
Because we need the control coming from here to the jump one.
Okay.
And that's based on the instruction. So 16 plus 3. So this is 16 and that's 19.
Okay.
So the larger is 19 plus 2 is 21. Okay. Branch unequal. That's going to be way less than 79, but let's do it. No, actually it's not way less. So what is happening? The branch unequal is my purple ink, which is, where is it?
Can you use the purple pen?
Yeah, my purple pen, yes, thank you. It is, so we're doing two things. One is we're doing a branch decision, which is coming out here, and the other thing is the actual branch target. So it could be the maximum of the two things. So let's do this path. Well, let's do this path first. 16 plus 8, 24. So this input is 24, this input is 26, because it also needs to go through the mux. 20, and this is going to be less than 26. So the larger of them is 26, plus 15 is 41. So this input is coming at 41. Okay? This input is coming at 2, way less than 41. So you don't even need to figure it out. So this input is at 41. 41. What's supposed to be 8? That's an 8, yes. Oh, sorry, 8. Okay, it's still less than 41. Okay, so 41 plus 2, 43, plus 2 more, 45.
Wait, what about the control?
Hold on. What?
What about the control?
Well, that's we figured out that that's going to be way less than 41. This is coming in at 41, and that's there's no way we can get 41. So that's stable way before 41. Okay. Okay. So now we figured out the paths on this this set of timing. So now we want to figure out our clock rate. Our clock, we can throw this away now. Our clock rate has to be long enough for the longest instruction. So our clock rate, clock cycle time, is going to be at least 79. I guess I could say greater than or equal, but I'll say equals. We could make it slower. So now the VLSI designer team, the VLSI design team comes back and talks to the system team and says, we can 79 nanoseconds happens to be 396. That's approximately 12.5 megahertz. If I did my arithmetic right, you can do it in a calculator and check. I'm not sure. Somebody correct me if I'm wrong, but I'm going to go on. So the VLSI team goes to the system team and says, our architect team gave us a design which will work at 12.5 megahertz. Is this what you want? Can we solve this? And the marketing team and the system team says yes or no. And then they go to the VLSI team. Typically in the first phase, the answer will be no, we want faster. And they go to the VLSI team, and the VLSI team decides that we need to make this faster. And the way they make this faster is not by changing the R-type instruction. They change something specific to the store word and maybe the load word instruction, because they're the pretty important term that I want to mention. This is the critical path. You want that, and so the VLSI team wants to change the critical path. In this case, there's not a whole lot they can do because most of the critical path is in the memory write. So either you make the memory write faster, or you don't do anything. Maybe you can shave a couple of nanoseconds here and there, but you want to save something of the pink path. And when you do that, maybe eventually you'll get the pink path down to 70. Now it no longer makes sense to change the store word. It makes sense to change the load word. So now you try to make the load word faster. And that's the back and forth. So the VLSI, sometimes the VLSI team will do it. Sometimes they'll come back to us, the architecture team, and say, make this get rid of that path because that path is too long. So we'll go back and forth for a couple of years between the VLSI team and the systems team and the architecture team, and try to get this get it as good as we can get it. But the key point is that at any one point, we only care about the critical path at that point. Don't try to change the jump at that time, because you're not changing. You haven't done anything. You're wasting time if you try to make the jump faster. Okay. So that is the end of the single cycle. Now we want to get faster. Yes. Now we want to get faster. What is the problem with the single cycle? The problem is that even if we're doing a jump instruction, we still need 79 nanoseconds because the clock cycle is for the longest instruction. In reality, what if? For these numbers, maybe I can get a 28 nanosecond clock cycle. R type will need 2 cycles. A load word, 28 times 3 is 84, so that a load word is 3 cycles. Store word is also 3 cycles. Jump will be 1 cycle. And the branch and equal will also be 2 cycles. If the instruction mix is good enough, this in theory could be significantly faster, and in practice also, it will be significantly faster than the single cycle, because for the 60% of the instructions that are R-type, let's say 60%, they will only need 2 cycles, which is 56 nanoseconds as opposed to 79 nanoseconds. So for the 10% of the instructions which are store word, load word, they will actually get slowed down, because the 28 times 3 is 84. So instead of 79, they're actually going to take 84. But that's just 10% of instructions, let's say. So if the numbers, if the statistics, if the averages work out, and they always will, well, they will not in this course, but in practice they always will. If the numbers, if the averages work out, then we will be faster by going to something that takes a different number of cycles, but has a fast clock. Everybody got that? Yes. And that is the whole point of multi-cycle. We make the average instruction faster, but the longest instruction will be slower, because the things are not perfectly balanced out. Because by going to, I guess we could have done 27 and a half in this case, but let's not. But even then, 27 and a half times 3 is 82 and a half. It's still a little slower than 79. So some instructions will get slower, but on average, it's going to be faster. And that is the point of the multi-cycle instruction, the multi-cycle architecture. Okay, so let's do the multi-cycle next. Okay. I'm just going to throw it out. What happened? The multi-cycle, what's going on?
Sorry, damn. Locking budget. Undo it. Undo it. Oh. Don't press the red button.
Oh, I know what's going on. I was pushing the book against the button. Well, pull the book away. I'm guessing that's what was going on. Okay, the multi-cycle was in an earlier edition of the book. It's not in this edition of the book. However, I added it. I posted both a link in the schedule, which Brightspace kind of makes it hard to get to, because they disable, they make you actually cut and paste. Or I also posted the actual section on Brightspace, so you don't need to follow that link. Up to you how you get it. But it's there. So I'm just going to give you the data. We're not going to design the data.
I think it's fine with this one.
Okay, how do we make things multi-cycle? We really make things, well, first of all, remember that sequential circuits are written on every rising edge. So we want to put a bunch of sequential circuits in the data pad. So we're going to add a bunch of registers. What are the registers we're adding? Something else I should say. Again, I said this earlier. Single cycle does not imply Harvard. That's just coincidence. But we are going to use a von Neumann architecture, not a Harvard architecture, meaning both memory and both data and instructions are going to go into the same memory. Again, that's purely coincidence. It's just the way we designed it. Nothing to do with multi versus single cycle. Okay? So we're going to add registers to enable running things in multiple cycles. First register is the instruction register. So we read an instruction from the memory, we stick it in the IR, instruction register. We add the A and B registers up here. That is for storing the results of the register file. So that's another cycle, from here to here. Another cycle, we add an ALU out register to store the result of the ALU. So going from here to here is another cycle. just take the A and B registers, do something with them in ALU, stick the result in ALU out.
Because there's no hair.
Another cycle goes from the ALU out into the register file. Or from the ALU out into the memory address. Or in case you're doing a store word, in case you're doing a load word, you read from the data from the memory and stick it in the MDR, memory data register. Another cycle goes from the MDR into the register file. So we've added these registers so that we can break an instruction down into multiple cycles. Okay? So now we're going to actually do this design. No, well, this is the data pack. We've done it the design, but now we're going to do the control. For multi-cycle, unlike single cycle, most of the designs will be in the control, not in the data. Because normally we try to minimize changes to the data pack. Sometimes we'll need minor changes like adding a mux here and there, but in general we will not be making large-scale changes to the data pack in the multi-cycle, as opposed to a single cycle where we're a little more free to make changes in the data pack. Okay? So let's start. As before, we are going to write not quite in English, but we're going to write formally, precisely, we're going to write what each of the instructions does, the R type, the fetch, and so on. So let us start. So now we need a desk with 3 sides, one side with this, later on one side with the control path, and one side with the instructions that we are going to be implementing. We are going to use a language, unlike single cycle, we are going to, which we used in English, we are going to use a somewhat more formal language called RTL, Register Transfer Language.
No. No. Oh no, it's
Okay, the idea behind register transfer language is that it's hardware, it's not software, but it looks like software. We're going to have a bunch of assignment statements and sometimes it's null statements, which on the left of every assignment statement is going to be which register is written, and the right of every assignment statement is going to be the function that we're doing. So let's do it. Fetch. So what is fetch doing? The fetch is going to be getting an instruction into the IR. Okay? So it's going to get, and I'm going to number these, I'll talk about that in a second. IR, the instruction register, gets something. What is it getting? It could get either the memory address by PC or the memory address by ALU out. For a fetch, which one do we want to get? ALU, well, what is an ALU out?
It stores the results.
Yeah, we don't have anything in ALU out at this point. We want the PC, whatever is in PC, to be the address that we're fetching. So we want mem of PC.
Right.
The mem of PC. So again, this is what RTL is. The left side of every arrow is going to be some register, and the right side is going to be some function of other register. No, not necessarily other, some function of registers. Something else we're doing for fetch. We're also adding 4 to the PC. Let's see, how can we do that? We're getting the PC coming here. That data path exists. There's a 4 coming in here. And we add PC and 4, and that data path back to the PC exists. So that's easy. All these data paths exist. PC gets PC plus 4. And I want to emphasize something also. It is very important. It's right. It's wrong if you don't. Numbering in the fetch case, there's only one cycle. But many of the things we write will take multiple cycles. I mean, it's a multi-cycle mix. So it's very important to number these things. Otherwise, the reader has no clue which cycle that happens in. In this case, both of these happen in the same cycle, so we just use the one number. But if this were a two-cycle thing, then we would write number 1, number 2. But absolutely, you are marked wrong if you don't have a number. So make sure you number everything correctly. Okay, so that's fetch. Decode. Well, actually, I'm not going to do. Yeah, let's do decode.
Lock it
On a RISC processor, as we've said many times, decode is trivial. So we're going to do some things that are not strictly decode because decode is so easy, but why waste the cycle to do very close to nothing? So we're going to do decode and register fetch and branch address computation. So we're going to add some stuff to the decode phase just because we don't want to waste time. Okay, so what is decode? Again, that's going to only need one cycle. The actual decode is trivial. So we're going to do the register fetch, which is getting something into A and B. That something is going to be the register selected by bits 25 through 21 and 20 through 16. So let's write that. A gets RF of bits 25 through 21 of the IR, the instruction register. So RF of IR of 25 to 21. B is very similar. RF IR bits 20 to 16. Okay, so that's the register fetch part. We also need to do the branch address computation. What is that? ALU out is going to store the target address. This might not be a branch instruction, so we'll just ignore it next in the future cycle if it's not. But the branch target address is going to be PC plus this PC relative offset. So it's going to be this field sign extended shift left 2 plus the PC, which is actually coming into here. PC is coming into the ALU. This thing coming into the ALU, the sign extended offset multiplied by 4, and we're going to add them and stick it in ALU out. ALU out gets PC plus shift left 2. What are we shifting left? We're shifting left the sign extended immediate field. Okay? The sign extended. What are we sign extending? Bits 0 to 16, 0 to 15 of the IR, the instruction register. So that is our RTL for decode plus some other things. now we have to write RTL for the execute for what? Okay. Now we have to write RTL for the execute for load word, store word, archive, jump, branch, and so on. So that's next.